So you want to design a signal chain. Well, you could search the internet, download a manual, and read through 50 odd pages, but that may or may not help. Because when did a PDF ever simulate a circuit? Or tell you that yes, your ADC can be driven by that amp you chose? Yep, never. Sure, design guides are great, but when you're getting into the nitty and gritty details of signal chain designing, they may not be the best route to take. But Analog Devices' Signal Chain Designer tool, well, that's something else entirely. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Matt Duff from Analog Devices and I walk through the steps involved to create an analog front end with Analog Devices' Signal Chain Designer. We demonstrate how you can quickly create circuits, simulate how the amplifier, filter, and ADC interact, and easily export to LTspice with this multifaceted tool. And before we get started, don't forget to click that link. There you can find even more information about this topic from Analog Devices. Hi, Matt. Thank you so much for joining me.
Hi, Amelia. It's great to be here.
Excellent. Okay, so what is this Signal Chain Designer tool? Matt, who is this good for?
All right, so we built this signal chain designer tool to help customers with precision signal acquisition. And so, you're an engineer, you're trying to, measure some sort of sensor, and you're trying to figure out the analog components to do that. And so we've created this tool to help you figure that out.
Excellent. Can you show me how it works?
So here is the tool. And we have a bunch of examples here, but I'm just going to start from scratch. So the first thing is I'm going to do is I'm going to pick a sensor, and I'm going to pick this voltage source.
So I see you have several things to enter in for this voltage source. Why do I need to enter in this information?
All right, so we have this measurement region, and if you put in some information about the frequency range that you're trying to measure, it'll make the tool a little bit smarter. It'll help us pick amplifiers. It'll help us determine your ADC driving. And then we've also got these output impedance characteristics. And you don't, sometimes with your sensor, you don't know exactly what the output impedance is, but you do know whether it's 1 ohm or a mega ohm or something like that. And so as we'll see here later, the output impedance of your sensor really does have a big impact on how your full circuit is going to work.
All right, so what do we have here?
All right, so I'm gonna use that, and then what I'm gonna do is I'm gonna actually create a signal chain here. So this is our area where we create the signal chain, and I am going to drag down an amplifier. And if I put in, say, a gain of 1, then it's going to generate a buffer circuit. If I put in, say, a gain of 10, then it's going to generate a non-inverting circuit. I can even put in a level shift, and it's going to generate that for me. So you don't have to go figure out what are the resistors, all this stuff. The tool's going to do this for you.
Excellent. Now, Matt, I see over there on the right, you've got a graph. What is that?
Right, so this is the transfer function of this circuit that we are looking at here. And if I change this pull down, we can look at other characteristics. We can look at things like the input impedance or the noise totals or the power consumption and so forth. And so something interesting is, so let's go to the noise totals. And if I move this slider, which is going to adjust these resistor sizes. So what I'm doing is I'm adjusting not the ratios, because the ratios would change my gain, but I am adjusting the kind of the absolute value of the resistors. Then that is going to affect my circuit and therefore affect things like noise, affect things like power. I've also got, and let's go to gain. I think this will be useful. So we also got this capacitance slider, and what it's doing is it's putting some feedback capacitance in here. And so you can see as I adjust the feedback capacitance, then that is affecting the gain response. The other thing that I can do is I can change my op amp. So I think we told the system that we needed like something like 1 kilohertz. And let's move that capacitor back here, and we can see that we're getting like 19 kilohertz out of the system. And so, maybe I'm like, hey, I want to go change my amplifier to something a little bit faster. I told the system 1 kilohertz, but I changed my mind. So I'm going to go in here, and let's say my favorite part is this ADA 4510-2. So I'm going to go change that, and now that's going to give me a lot faster frequency.
Okay, so Matt, I see you're doing all of these different simulations, but why wouldn't I just do this all in LTspice?
Yeah, so LTspice is the tool that's been around for forever, and it's a fantastic simulation tool. And the great thing about doing this is that you can, and I'll show you in a minute, you can export to LTspice. So you can export any of these circuits to LTspice. The big thing about this tool is that it is generating these circuits for you, and then we give you some simulations so that you can see in real time how these circuits perform. All right, so let's say, that's about LTspice. So let's say we're happy with this amplifier circuit, and we can go back to our main screen. So here's our main screen. In fact, I'm actually not, there's a big old peak in this amplifier circuit, so I'm actually not very happy with it. So let's move our resistors down a little bit so that we have a little bit better response. And we just have one part in here. We can see the response here, but let's add another part type, and we can see how that performs. So I'm going to drop this ADC, and I'm going to ask the tool for 16 bits, and I'm going to ask for, let's say, 2 megasamples per second.
Matt, I think you may need to get better at your demo skills. You've got a big error there.
Yeah. So what's happening is that this is actually intentional. So the previous amplifier that we asked for can't actually drive this ADC, and so the tool is when you have an amplifier and ADC, the tool is going to check for you and see if the amplifier can drive it or not, and if not, it's going to warn you. So what we can do is we can go back to the signal chain. And one thing we could do is we could go into our selection here, and we could pick a faster amplifier. I'm actually going to be a little lazy here, and I'm just going to click on this guy here, and it'll give me the option to insert a buffer. So I'm going to insert a buffer, and the tool is going to pick a nice fast amplifier. Let's see, this ADA 4807 that works well to drive this ADC. All right, so now we've resolved that error. We're in our ADC stage, and we can see that we have similar performance graphs to what we had for the amplifier stage. And you'll notice that not only did the tool give us an ADC when we asked for this 16 bits and 2 megasamples per second, it also gave us a reference and a RC filter, so that typically with these higher performance ADCs, you're going to need these other components, the other reference, the filter, in order to get the good performance out of it. So I've got I put it in a single-ended configuration. And so now what I'm going to do is I'm going to show we can put it in a differential configuration. And so now we have this differential, and that'll help us get a little bit better signal to noise ratio. So I've changed this box to give us that differential capability.
But Matt, isn't that going to break your circuit? Your amplifier before was single-ended out.
Yeah, that's exactly right. That's exactly right. And so if we go back to our main signal chain, we can see exactly that. And so what we can do now is I'm going to change this single-ended. So I go into this configuration, our amplifier, and I'm going to change it to single-ended to differential. And now you can see that it is creating a single-ended to differential circuit using a differential amplifier. One of the other nice things it's doing is it's making sure that the common mode out of this amplifier is what we need. So I'm going to use that. And as we have been going through this, we've actually been building up a little circuit. So let's look at what we've built here. So here's our first stage, here's our second stage, and then here is our ADC. And now that we have some capability, we can go look at things like the input range. And look here, so here's something interesting, is that the tool kind of defaults to plus minus 1 volt. And we have this input range of negative 498 millivolts to 99 millivolts. So it's telling us this is what our input range is. I'm just going to pretend for a moment that our input range is like plus or minus 50 millivolts, so we don't have that error. Oops. But we could also go and we could modify things to change it. The other thing we can do is we can go look at other performance. So we can go look at, say, the power consumption. We can go look at things like the noise. So just like what we had in the stage views, now we have at the signal chain level.
That's pretty cool, Matt. But what if I want to change the performance?
Well, so if you want to change the performance, then we go and we modify the circuit to change the performance. So, for example, right now we have this bandwidth of about 842 kilohertz, and that's way, way higher than that 1 kilohertz that we talked about. The other thing we can look at is we can see that we have, let's refer this to input, we have about 20 microvolts RMS noise. And so, one way that we could modify this is we could add some filtering to both lower our bandwidth and lower our noise. You want me to show you how to do that?
Sure.
Okay, so what we can do is we can add an analog filter, and there's a couple of different ways that we can do filters. So one way we can do is we can go in and just do a single stage type thing. If we were doing a more complicated filter, let me show you how to do the more complicated, and then we'll come back to the single stage. So if we're doing a complicated filter, I can actually launch this filter wizard tool. So if I'm doing like a single-ended type filter, so this tool won't do differential, but it'll do single-ended, I can then go put in some information about the filter. It's going to generate a circuit for me, and then I can go through and I can see like how are the tolerances of my components going to affect me. I can do all this stuff, and then when I'm happy with it, I can send that filter back to Signal Chain Designer, and now that filter is now in Signal Chain Designer, and I can use it that way. So that's one way to do a filter. Another way, especially if you're doing like a differential filter, is you can actually go in and just do it yourself. So I'm going to do a single stage here. I'm going to do like a low pass. I'm going to do like a second order. And I didn't even pay attention to what that other filter frequency we said. So I think we were aiming for like 1 kilohertz total. So I'm going to give us 2 kilohertz just to give us a little bit of extra margin there. And that is going to generate, this looks pretty complicated, but this is a multiple feedback filter with the right common mode adjustment out. And so we're going to use that filter. And now we have dropped I would have said that we had dropped our noise. So we were going to drop our noise, but that filter looks like we have, it itself is messing up our performance. So what we're going to do, so what happened is that we had, this part has current noise, and that current noise flows through those kind of big resistors that we had before. And so here, let me show you. So we had this, we put in this filter, and what we're trying to do is reduce noise. And look, we have this massive noise increase from this filter. So we got to go fix that. So what I'm going to do is I'm going to go into that filter, and I'm going to move this slider that sets my trade-off between my resistors and my capacitors. So what I'm doing is I'm making my resistors smaller, and I'm making my capacitors bigger, and that should get rid of this big old noise that we had before. And so now I'm going to do that. And now I've whacked down the noise of that filter. And so now instead of that 20 microvolts that I had before, I've got 12. Now, one thing to note here is that our ADC is the dominant factor. So I filtered out all the noise of the other stuff, but our ADC is the dominant factor. And so really when you need to filter the noise of the ADC, the way you do that is with a digital filter. So we're going to put in, let's say we're going to put in some averaging filter, and let's say I'm going to do, let's say 128, no, actually 256. So I think all right, so that's like 3.4 kilohertz, something like that. And now that really lowers our total noise from like that 12 to something like that 4.63. So you can see all the various different filtering options that the tool allows us to do to reduce things like noise.
So, Matt, you've shown us a lot of simulations in the tool, but how does this compare to LTspice?
All right, so let's just go look. So I'm going to go to next steps, and here is our LTspice simulation. And now I'm going to open it up. Pull this window over here. And here is our schematic in LTspice. So if I zoom in, here's that original very first stage that we did with the level shift and the gain. There is some of our, I think that was our driver circuit maybe. Here is that filter wizard filter. Here is that differential filter. Oops, no, that's a driver thing. Here's our differential filter. There's our ADC, and LTspice doesn't do digital filters, so it just says, hey, look, we didn't do the digital filter, but lets you know that this is where it would be. So that's how you see it in LTspice.
So, Matt, I saw the other button to save or share the design. How does that work?
So, yeah, so this button right here. So what we do in the tool is every time that you go return to the main screen, we save a snapshot. And so this is a snapshot, and I'm going to copy that URL to the clipboard. And so then I could open up another tab, and that would then load that design that we just did. And so you can take that URL and you can save that URL if you want to load the design next week, or you can send that to a colleague. Note that this is it's a snapshot. So if you send it to a colleague and that colleague then goes and works on it, you're not going to see their changes. And the same thing, if I keep working on it, that colleague is not going to see my changes.
So if I send it to somebody else, they can't mistakenly mess up my design?
That's right. Exactly.
Okay. So, Matt, this tool looks pretty fancy, but I guess it's only as good as its predictions. So, how do I know if its predictions are any good?
Well, so first, this is coming from Analog Devices, and so we know some things about how to do these things. The other thing is that we put various help topics throughout the tool so that you can better understand exactly what we're doing. So we have all these little question marks, and so the question mark is going to give us a bunch of help information on how to do things. Let me show you another one here. So here's this DC error, and in DC error, what we're doing is we're showing this information about how we computed, for example, the bias current drift, or I think CMRR shows you how we think about CMRR. So you can get a lot of information and feel confident that we're doing things correctly. And then the third thing is we are still in beta. So there are still things that we are checking and working on, and we're proofing to make sure things are working correctly. And so if you see something that looks weird, or you're not quite sure about, or seemed like a bug, we have this feedback button. And so please press this feedback button to let us know if you see anything odd in the tool.
So let's talk about data comparison. Now, Matt, how does Signal Chain Designer compare to LTspice in terms of simulation?
Well, so we have this slide here, And we have a comparison of Signal Chain Designer, the data sheet, and LTspice. And so it depends on the model, and sometimes we get it right and sometimes we don't. And so we're working through, part of the reason we're in beta is we're going back and we're checking all these things. But here's a typical part. And you can see that both LTspice and Signal Chain Designer match pretty closely the data sheet. Although it's interesting, you'll also notice that they are not the same. So we are using a little bit different modeling technique in the tool. We are using a 4-port network modeling technique that allows us to be very fast and we don't have any convergence problems, but it is a little bit different technique than the nodal analysis that LTspice does. And so you're going to get a little bit different results, but in general, we are going back and checking so that we are matching very well to the data sheet.
Fantastic. So, Matt, before you go, can you recap your main points for me? What would you like my audience to take away from today's Chalk Talk?
All right. So what I want them to take away is we have this great new tool to figure out how to design precision signal conditioning circuits. And so the things that the tool does is, one, it helps you create circuits very quickly. So we showed in the beginning, you put in a gain of 10 and it just generates all those resistors for you and you don't have to do the math. So it allows you to very quickly cycle through different circuits, different iterations, and see what you're going to get. The second thing it does is it simulates those for you so that you can have faith that whatever you're picking here is going to work well on your bench, and it simulates things that maybe are hard to simulate in other tools. For example, driving an ADC and making sure that the ADC can actually be driven with the amplifier. And then the third thing is that you can export to LTspice. And so you can export to LTspice because you know it and you want to check the design. That's one reason. Another thing is that our goal with Signal Chain Designer is to help design very standard circuits. So the standard circuits that you might have learned in school. But we're not going to do some sort of esoteric circuit that maybe is your secret sauce. And so you export to LTspice, and then you can add, say, your inductor in some weird spot or whatever. So the idea is Signal Chain Designer, do 80% of your work extremely quickly, and then export to LTspice for fine tuning.
Excellent. Well, Matt, I think that's all I have time for today. Thank you so much for joining me.
Oh, thank you, Amelia, for having me. I appreciate it.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Analog Devices. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.